Identifying phase transitions on a heating curve. So a heating curve is essentially showing temperature against heat added, okay? So they all are going to follow a very similar kind of shape, okay? So what is happening if we start at the 0 point, right at the origin, as we add heat, all that heat is going into raising the temperature of the substance. The substance must start as a solid, okay? So at the lowest possible temperature, the substance is a solid. So this, I'm going to call this like phase one, stage one. Okay. So stage one, all the heat is going into raising the temperature of the solid. So if you want to work out what Q is that's associated with that, it is going to be related to the specific heat capacity or the molar heat capacity of the solid. So would you use Q equals M CS delta T to work that out, bearing in mind the units of specific heat capacity are joules per gram per degree Celsius, which is why you multiply by the mass and you multiply by the delta T to give you Q in joules, okay? Alternatively, you might use Q equals N times Cm delta T, where Cm is the molar heat capacity, just different units for the same thing, which is joules per mole per degree Celsius or mole per Kelvin, same difference, right? In which case you'd have to multiply by the number of moles of your substance in order to cancel out moles and degrees Celsius to cancel out Celsius and end up with an answer for Q in joules, okay? So once the solid gets to the melting point, then you're melting, right? Melting and boiling occur at constant temperature because all the heat being added is going into increasing the kinetic energy of those atoms or molecules in the solid state until they can escape from the constraints of the solid phase of matter. So that energy is going into melting, essentially. So for stage two, that is going to be melting solid at constant T. So wherever you see those isotherms where you're at constant T, that is a phase transition that is occurring. Okay, if you want to work out for Q, what that is going to be related to the enthalpy, so delta H of melting, which is delta H of fusion. So if you multiply that, because delta H of fusion is in kilojoules per mole, multiply by that by the number of moles of solid you actually have to get Q. Usually that's going to turn out in kilojoules because delta H of fusion is in kilojoules per mole. So just be aware of that. Okay, so that's stage two. I'm going to have to go back and forth to kind of label this, aren't I? Okay, fine. Stage two. Okay, stage three. I'm just going to go ahead and label all of these so I don't have to go back between multiple text boxes. Okay. Okay, new text box then. Okay, so stage three, try and line this up as best as I can. Stage three is raising the temperature of what is now has been melted of a liquid. So you're going to treat it in the same way that we did for stage one. You're going to use the specific or the molar heat capacity of that said liquid. So Q equals M CS delta T, or alternatively Q equals NCM if you've got the molar heat capacity delta T. All right, so what's happening at stage four? We see a straight line again, isotherm, constant temperature. So you're boiling your liquid, a phase transition happens at constant temperature because all that heat energy you're putting in is going into giving the liquid molecules enough kinetic energy to have more degrees of freedom and be gas molecules now, okay? So Q for that is going to be related to my delta H of vaporization, the enthalpy change associated with boiling a liquid to form a gas. So that'll be in kilojoules per mole. So if you need to know the total amount of Q, you probably will have to multiply by the number of moles of liquid you actually have. Interesting thing to note, line 4 is much longer than line 2. You have to add more heat to boil a liquid than you do to melt a solid. Think about the difference in density between solid and liquid, liquid and gas, right? Gases are way less dense, have far more degrees of freedom than a liquid. So the energy difference between the gaseous and liquid phase is much bigger than between the liquid and solid phase. Therefore, line 4 is much longer. It literally takes more energy to boil liquid than it does to melt a solid. And then lastly, 0.5, you have a gas, you're making it hotter. So we're just raising the temperature of a gas. So again, Q is going to be related to the specific or the molar heat capacity of said gas. So you can If you have a heating curve, you may be asked about just one portion about it. You might be asked about the whole thing. You have to break it down and actually look at what you're being asked. So to read what's going on with this guy, what is the boiling point of X? We need to understand that line 2 is going to be melting point, line 4 is going to be boiling point. So we're just going to extrapolate back to our y-axis so we can actually read that. Didn't do a great job of that, but here we go. Each of these must be 10 degrees Celsius, so it's probably like 58 degrees, something like that, as well as I can read it off my computer screen. Okay. What phase, physical state, would you expect to find after 34 kilojoules of heat have been added? So I'm assuming that's from 0. So again, each of these 2, 4, 6, yeah, these are 2 per. So 34 kilojoules would be here. So let's see where we intersect. We are at the boiling point. So after we've added 34 kilojoules of heat, we are still boiling. So we would have a boiling liquid, essentially. So that would be where we would be at on that particular plot. So if you find yourself like actually on a phase transition, if you're actually on a phase transition, what does that mean? So that means that you have made quite a bit of gas, right? But there is still some liquid remaining. So in this case, it says check all that apply. So I would go ahead and check both the liquid and gas boxes for this particular point. If we'd been given something that was like, I don't know, 8, okay, if 8 kilojoules per mole been added, then again, you would have some solid remaining and have some liquid that's been formed. So I'd check solid and liquid. If I ended up on one of these curves here, so say I'd got 38 kilojoules per mole had been added, well, that clearly puts me in the gas zone, so only gas would be present. Okay, so hopefully that is helpful to you guys for interpreting heating curves. So you've just got to really carefully look at what information you're looking for. They're all going to have about the same sort of shape. The actual lengths of the lines may vary depending on the specific material, but they're all going to have the same positive gradient, isotherm, positive gradient, longer isotherm, positive gradient kind of thing going on.